So we got the phasors, right? So this green arrow is basically, we're visualizing that it would be rotating counterclockwise at 60 cycles per second, or 60 complete rotations per second. But when we describe a voltage or a current as a phasor, we're just taking a snapshot in time, and that time is arbitrary, right? So in any situation where we're relating multiple phasors to each other, we have one choice of coordinate system. We can make one of the phasors, we call it angle 0. And then all of the other phasors are going to be measured relative to that. So there's this 1 degree of freedom of when I... okay, so hold on. Carl is trying to join, and he has to be let in. Ben, can you let Carl Blumstein into the meeting?
I can, although nothing popped up on my screen.
Hold on one sec. I just really, Carl was trying to join this. Therese, can you help Carl out with this? You're muted.
Yes, I can.
Please. Okay, thank you. So yeah, Carl is texting me. If you could text him back, Therese. So what we're trying to do here is we're trying to relate multiple waveforms to each other. And there are two different kinds of phase angles that we're interested in. One type of relationship is between different... hold on one second. I'm trying to multitask. One is between different voltages at different locations in the grid. And this is something that's totally not obvious if you're not into AC power, which is that even though the voltage is synchronous all across a connected AC grid, there's actually a slight change in the timing, in the phase, that's related to power being transferred from one location to another. That is not obvious, but it's the thing that synchrophasors or PMUs are measuring. And that you have to have a common time signal from GPS or other shared high accuracy clock in order to accomplish, because the difference in timing we're talking about is very tiny fractions of a second. Now, the other type of angle difference that we can represent with phasors are differences in timing between current and voltage. And that we talked about last week. We are interested in the phase shift between current and voltage because that describes a power factor, and that's associated with reactive power circulating through the system. So these are two physically very different types of considerations. One is the difference between voltage and current that's related to the power factor. The other is the difference between voltage in one place and voltage in another place. And that's related to long distance power transfer. Over short distances, you would barely be able to measure. That's why we have micro PMUs, a timing difference of just a degree or so. Over long distances, that becomes important. And measuring the phase angle difference between a current and a voltage is something that you don't need a GPS clock for because you're in the same location. So your measurement device has one local clock that it can use. So that's not too complicated. So this is just, summarizing, that's the waveform that we're representing. Now here's a picture I didn't have last week, and this is showing something familiar to those of you who have looked at voltage phase angle or current phase angle data and said, what the hell is going on here? This is so weird. So the upper part of the graph is when you are looking at a single channel of measurement against the clock, and it will show basically the phasor wrapping around, because the way the PMU is configured is that if the frequency is exactly at 60 cycles, your green arrow is going to appear stationary, so that angle would stay constant. But given that, so everything is computed on the basis of an exactly 60.00 hertz frequency. Because frequency in the grid is not exactly 60.00 hertz at all times, you will see as an artifact that phase angle increasing or decreasing, depending on whether the frequency is greater than or less than 60 hertz. And it's when the slope is 0, when it's flat on top, that was the moment that the frequency was exactly 60 hertz. So you see this wrapping around from 0 to 360 degrees, and you could actually compute the frequency visually from seeing how fast it wraps around, right? How many seconds it takes to wrap around and get a complete cycle ahead of itself. There's, of course, apps inside the PMU or in the database that can do this and extract the frequency out of the raw phase angle. But visually, this is not super informative. But if all we have is raw phase angle data, then if we're plotting two different locations on the same graph, what we're going to see is that there's a slight shift in where they wrap around. And that, of course, is exactly here the shift of a few degrees between these two PMUs. Any questions on this? Okay. So usually, in order to have a physically meaningful piece of information, what we want to do is we want to take the difference between two locations and then plot that as a difference, which we did in the original Berkeley tree database right here. So these are, you see 6 traces. These are 3-phase voltages at 2 different locations. There's 3 flavors of blue and 3 flavors of red. Those are phases A, B, and C. Blue in Berkeley, red in Alameda. And what we're showing here is you see that the phase angle doesn't hold constant, right? They all kind of drift a little bit upward, which tells us the grid frequency was a tiny bit greater than 60, not much, at that particular time in 2017. But we're not interested really in the absolute angle. Here we're interested in just the disturbances to the angle, because in this picture, I took the screenshot because I wanted to show that this allows me to figure out which phases A, B, and C are matched to each other at different locations. If I were to call up PG&E and ask them, they wouldn't be able to tell me because their phase labeling is awful, like many other utilities. It's, basically, it was hard to have an instrument back in the day to sort of connect and tell you what's A, B, and C, again, because you don't have a common reference clock. So they just sort of went with the label when they installed it. And then after a storm, some stuff gets reconnected and it gets moved around. So mapping of phase connectivity is actually a problem for many utilities. But you can see that with these 2 micro-PMU measurements, it's pretty straightforward during a disturbance. And I just had to scroll through the data to find a day that there was a nice disturbance. I can match the bright red and bright blue phases are disturbed in the same direction. The dark blue and dark red are in the same direction by a lot. And the gray, blue, and pink are disturbed in the same direction by a little bit. So that perfectly lines up phases A, B, and C for me. And that's between 2 locations that are pretty far away, that are not on the same distribution system, but they're connected by the transmission system. They could have a few delta Y transformers between them, but this aligns pretty nicely.
Would you,
yes.
for these types of disturbances, would you expect to see those kind of the direction of the disturbance mirrored across phases like this?
Yes. So presumably the disturbance happened some place distant. It was a fault somewhere. That's almost always what it is. And during that fault, there was just a swing. It was, an asymmetrical fault or unsymmetrical fault.
Mhm.
And, so phase A got disturbed in the forward direction pretty much everywhere, in California.
Yeah, interesting.
Now, I could use high resolution voltage magnitude measurements to do the same thing, but not quite. So we see that the magnitude measurements alone, without the timing, they also match the gray blue to the pink, but they don't really allow me to resolve which of the medium and dark blue and red go together. So there's a little bit of ambiguity there. So the phase angle is more decisive, really, as an indication. But having said that, matching voltage magnitude disturbances from different locations, if you have sufficiently granular data, is a pretty powerful tool. And a lot of the work that Mohini has been doing with analytics, with our micro-PMU data, is basically doing fancy statistics with correlating these voltages and their disturbances. And that is all made possible by the time alignment and the fact that we got 120 samples per second here. You couldn't do this if you just got data once every second, or probably even 10 times a second would be hard to get this kind of confidence. So I had shown you last time that in going from a three-phase system to an actual plug, you always have to sort of pick two places to connect to. And there's fundamentally two strategies for doing that. One is to connect between two phases, AB, BC, CA, or connect between any one phase and a neutral point. And the neutral, for our purposes, is basically the same as ground. Now, in practice, engineers worry a little bit about, how close to ground is the neutral really, because during a fault, some bad stuff can happen. And also, if you're making a very high precision measurement, you care about the few volts difference between neutral and ground. But, somewhere that neutral is grounded. So we have a delta version and a Y version of connectivity. And what I didn't show you last time, because I said, well, we got to talk about phasors first, is some diagrams of how the three phases in voltage and current relate to each other. So for a Y connection, basically we would draw the three voltage phasors like this, where they have all, in a balanced system, the three phases have the same magnitude, we assume, and they're 120 degrees apart from each other. So in this trio, one of them, we're setting phase A to 0 because we choose a coordinate system. We press our stopwatch at the moment that the red phasor crosses the 0 axis. And so then we assume that everything is in a steady state. Everything rotates counterclockwise at 60 hertz together, but we don't have to depict that because we're taking a snapshot in time and we're doing a steady state analysis only. We are not interested right now in the fact that these things in real life wobble around and do crazy stuff. So in a delta connection, where we are connecting between two phases, the voltages represent the difference between pairs of phases. And there's still three balanced voltages, 120 degrees apart. But if you do your vector addition or subtraction, which is sort of convenient that we've converted these time-varying quantities into something that you can analyze graphically by its length and direction on a piece of paper, we can do this vector addition here. And we can say, okay, the voltage between phase B and neutral is the difference between the voltage between phase A and B and the voltage between phase A and neutral. So we're applying Kirchhoff's law here graphically, and we can show the relationship between the line-to-line and the line-to-neutral voltages. So this motivates the fact that we're going to see a 30-degree phase shift between them. And there's also that factor of a square root of 3 that I talked about last time without deriving it. But from the phasor diagram, you can do a little trigonometry and work that right out. So the upshot is, if you're connecting something between a pair of phases A and B, you get a bigger voltage by a factor of √3 than if you connect something between one phase and neutral. And there's also a phase shift, which you can draw pictures to remind yourself if it's plus or minus. The same is true for currents. Now, the currents in a delta configuration are going to be counterintuitively smaller than the currents in a Y configuration. The reason that has to be true is because energy is conserved and voltage times current is the same thing. So if you go to a delta connection, you're getting a bigger voltage, you would correspondingly get a smaller current. And you can again do the vector addition in the complex plane here and see that the current that goes, for example, from phase C into phase A is, by Kirchhoff's law, the sum of the line current going into phase C plus the current from B to C. And this is all a little confusing, but you got the slides and you can play with this. There's nothing magical about it. It's just, vector arithmetic here. Questions about this? Hearing none. Moving on to symmetrical components. This will get you a lot of bang for the buck of sounding like you know what you're talking about in power systems for not very much math. And we're not going to go too far into detail. If you're mathematically inclined, you can play with it and it'll make perfect sense. And if not, the takeaway is this. There is a very concise representation of three-phase voltages and currents that basically separates your three pieces of information into information that tells you about the balanced condition of the system, that's the positive sequence, plus two pieces of information that tell you about the distortions of your three-phase system. And I really shouldn't say three, I should say six, because each phase has two pieces of information, right? So voltage phase A has a magnitude and an angle. Voltage phase B has magnitude and angle. Voltage phase C has magnitude and angle. That's 6. Now, one of them we can choose by choosing our coordinate system. So, but don't worry about that. So these 6 pieces of information can be represented in this context of what are called symmetrical components that are 3 trios of phasors, which by definition, these sequence phasors have the same magnitude. So the trio of positive sequence phasors have all 3 the same magnitude and are 120 degrees apart. So if you've defined what VA positive is, you've defined what VB and VC positive are. And in a balanced system, that's all there is. Now, when you have distortion in the system, because not the same number of customers are connected to each phase, some streets only have phase A. And in our EcoBlock project, we have just all the customers on one street on one phase. Naturally, when when you haven't done a lot of statistical aggregation like you have at the transmission system, in the distribution system, you expect there to be discrepancies. And there could be like 10% discrepancy in current, usually just a few percent in voltage. But those mathematical distortions of the positive sequence situation are mathematically captured by having some non-zero negative sequence component, again, a trio of balanced phasors 120 degrees apart, plus what's called a zero sequence component, and those are all pointing in the same direction, same magnitude. So if you want to represent an actual unbalanced system, you can represent that mathematically as a recipe that consists hopefully of the main ingredient being positive sequence, and then a little bit of negative sequence and a little bit of zero sequence added to the recipe to distort things, right? It's like the bread is mostly flour, but it's a little bit of salt and a little bit of yeast or something like that. So here's an illustration of how, the three sets of sequence vectors would add up to create 3 unbalanced phases. And in this case, what you can see is that for the red phase, the 3 components kind of all go in the same direction. So when you vector add them together, they tend to reinforce each other. So the red phase is bigger. Whereas with the yellow and the blue, you get a little bit of cancellation because you got components that are pointing in opposite directions. So the vector sum is a little smaller. And if you're into math, you can, work this out with linear algebra, and you can write it with coefficients. You can put those coefficients in the complex plane, where this alpha basically means a rotation. And then you can, write all 3 sets of vectors in terms of a matrix. The same is true for currents, and you can go backwards out of the phase currents. You can extract the 0, positive, and negative sequence currents. And this is stuff that PMU, firmware or software will do for you. The relevance of symmetrical components is that you can do very tidy analysis of 3-phase systems. Instead of taking into account all the cross-referencing relationships between and among all the phases, which basically would mean writing down 9 equations, you can represent the system in terms of the sum of 3 balanced or symmetrical systems. So it makes the math easier. A lot of PMUs are reporting from the transmission system where phase imbalance is not usually very interesting. They will report only what's called a positive sequence quantity for voltage and current. And basically what that means is from 3-phase measurements, or it might even just measure a single phase. Usually it'd measure all 3, but it won't be reporting back all 3 phases individually. It might just say, we've looked at 3 phases, and yeah, there might be a little distortion, but we're telling you what the positive sequence component is, which is the dominant component, so that should be approximately right. And the more, as I said, statistical aggregation you have at the transmission level, the more valid is the assumption that the system should be balanced, and the positive sequence should be very representative of everything there is. In the distribution system, it's almost always necessary to do an unbalanced analysis, so to account for these negative and 0 sequences in order to see what's going on. Questions on this?
And for distribution systems, would you typically get these different sequence components reported back, or would you get raw measurements?
Well, typically nothing yet, because typically there won't be so many distribution PMUs out there. But I guess more often than not, you would just get individual phases. So if you wanted symmetrical components, you'd probably have to write your own code to compute them.
Okay. And then for phasers that would just report positive sequence vectors, it seems like there's information loss associated with that. What happens when there is a disturbance?
You can't see it.
Oh no.
So that's our second category of lossy compression, right? So it's information loss from the phase imbalance, and we already lost information when we chose to represent the waveform as a sinusoid, because in reality it's not a sinusoid. So everything that's in there in terms of harmonics and distortion and other imperfections is not going to be captured.
Interesting.
Is
that standard?
That's something that grown men are crying and arguing about as we speak, because there's people who are saying the industry needs a standard for how to report things that are not sinusoidal. And there hasn't been historically an infrastructure for doing that, because streaming phaser data alone has been thought of as a big deal in terms of information transfer, a bandwidth required and storage required. So when you now go to point-on-wave measurements, continuous point-on-wave measurements that tell you all about the waveform, that's another, order or 2 orders of magnitude more data. Now, one way around this, and you should, if you're interested, read Harold Kirkham's stuff from PNNL. There are ways to improve upon this information loss by defining phasors in a way that describes sort of a best fit to a variable frequency, and also reports a goodness of fit measure. So you can still just report 1 or 2 frames per cycle, but with each frame, if you do the phasor computation a little differently, you can, first of all, maybe have a little more fidelity, intuitive fidelity of what happens when there's step changes. And I will say there's no absolute mathematical fidelity, because a phasor is simply not an object that's defined when the frequency is not constant, right? So there's no right or wrong answer here. But you can report some number that makes intuitive and practical sense. So we can follow up on that. Other questions? Moving right along to the per unit system. That was something that was, I think, on Ben's list originally. The per unit system is not rocket science, but it's confusing if nobody told you what it is. So this will not take long. The per unit system is a way to express measured quantities relative to what would be sort of an intuitive 100% value. So that base value, which is your intuitive 100%, would be like the rated capacity of a transformer, for example. And it would be the rated or nominal voltage for the section of the system that you're on. Now, for example, that rated voltage will not be exactly the operating voltage. Let's say that the nominal voltage at my house is 120 volts. So I would call that the base voltage. And then let's say that I measure the voltage and it's 118. So I can say that, well, in per unit, my voltage is 118 divided by 120. So that's 0.99, whatever. So that per unit value gives us a very meaningful metric of percentage-wise, how am I doing here? Am I at the nominal? Am I a little below? Am I a little above? Or in terms of power, it would say, well, what percentage of my load, of my rated capacity am I using here? So when you're doing actual circuit analysis, it's really when you have transformers that you need the per unit system, because you will have power going into a transformer with 1 voltage and 1 current on one side, and come out of the transformer with a different voltage and a different current on the other side. And what you're doing by expressing them in per unit is you're making them the same, because you're choosing different base values on either side that correspond to the voltage step up or step down. So it's really just a scaling is all it is. And then there's a bunch of convention about, well, how should you choose the base value? And we don't really have to go into that. For doing the arithmetic, basically there's 2 choices you make. You choose a base value of voltage for any region of the system that's at the same nominal voltage level. And then you choose a power base value. So S is apparent power. And it's going to be the same for real and reactive power. And that base value for power is going to be the same throughout your analysis, throughout your system, because it stands to reason that anything that's connected together should not be orders of magnitude different power capacity. So you then will have a different base voltage on different sides of each transformer. You could have many zones within the big homework problem. And you then can express all the quantities in terms of these base values. Your base values for impedance Z and current I will be determined by your choices for S and V. So they'll be different. and per unit doesn't change the angle, preserves the angle of phasors. It'll scale the magnitude of your phasors. And the nice thing is that to the extent the transformers are ideal, if they don't have losses, then they just disappear in the per unit system, and it makes the analysis of large interconnected systems much easier. When we talk about voltage sags, and let me go back to the empirical example that we had here, you see that there was the same voltage sag, the same event observed in both Berkeley and Alameda. But I would say, well, in Alameda, the voltage sagged by like 250 volts or something. And in Berkeley, the voltage sagged by like 2000 volts. How does that make sense? Well, it sagged probably by about the same per unit value. Because if you look at the 2000 volt sag here and divide it by the nominal or base voltage, that here would be like 7.2 kV or something, you would get some per unit value. And the same thing if you divide this voltage sag by the nominal value in Alameda, which was 280 volts. So describing a voltage sag in per unit is a wonderful way to just keep a consistent metric regardless of where in the system you're measuring it. Questions on this? Moving right along then. Frequency regulation. So this is a picture that Alex McEachern shared. He uses this in a lecture about frequency regulation, and I love it. So I stole it. And it is basically some, old-fashioned factory thing. I don't know what they're making, but they have these machines there, and all of them are being rotated from the same shaft. So there's this shaft running along the ceiling that's spinning at some frequency, and then you have belts that can either drive machines for whatever it is maybe they're weaving something, or you can use a belt with a motor to drive this shaft rotation. And what makes sense intuitively is that this shaft is going to rotate at a constant speed if the amount of power that you put into spinning it is equal to the amount of power that you take out from it by driving these machines. So Alex, being Alex, got to work in his workshop and built a little model of this. So we have a common shaft, and we have a motor that turns it, and then the belts turn these other motors. And what Alex illustrated here is, and he wanted to, I don't have a picture of it, put some pins on this rubber shaft to show that as you're transferring power through the shaft actually twists a small amount. Now, a steel shaft is going to be fairly rigid and it won't twist very much. Alex built this one with a rubber, and he decided actually he needed to use a different variety because this one twisted a little too much. But that twist in the rotating shaft is analogous to the voltage phase angle that varies depending on whether you are driving the rotation at a particular place or bus where your generator connects, or whether you're sucking power out of the grid at that location. So in the places where the shaft is doing work on the exterior, it's going to be lagging. The voltage is going to be a little bit behind. And depending on the stiffness of the shaft, and that stiffness is the metric for that in the grid, is the electrical impedance. And you can also appreciate is that if there's too much twist, or there's too much soft rubber, or the shaft is too long, then you're going to lose synchronicity between and among the devices. And that was one of the questions that came up. So in the perfect homeostasis, in the equilibrium, we expect that the shaft is spinning at exactly the nominal frequency. The same amount of power is being taken out that's being put in, and there's going to be a steady amount of twist, but not too much, a few degrees. So I like this visual aid a lot. Here is a more common, any questions on this? Here's a more common and less powerful way to visualize frequency control. And that is using water as a visual aid. And the analogy here is that we have a water level that stays constant if the frequency is constant. If there is more generation than load, in other words, we're driving the system harder than we're extracting power, the water level will rise. And if there's more load than generation, the water level will fall. The object is twofold, and there's two objectives that we must distinguish. One, we want to hold the water level constant. We don't want it to be rising or falling very quickly. Two, we would like that constant level to be near 60 hertz or 50 hertz if we're in another country. So having the frequency be constant is the first goal. The second goal is, yeah, it would be nice if that constant frequency is near 60, because that way all the clocks will run on time, and that way all our economists and accountants will agree on, who's produced how much power, because we use the frequency to keep track of exports and imports, and we can talk about that another time. But there's physically in the system actually quite a bit of tolerance of where we could be, what constant frequency we could be operating our grid at. There are relay settings that whose choice is somewhat arbitrary, and it varies depending on engineering culture in different locations, even within the same country. But how far below 60 hertz do you have to go before you start to open circuit breakers and say, this situation is bad? Clearly, we have lost a big generator. We need to shed some load so that the frequency doesn't collapse, so that we don't have a cascading blackout. So somewhere at 59 point some degree, some relays will start to open up, and that is a bit of a subjective choice. Same thing if you have over frequency, because your generators could get damaged if the frequency were too far off. And then once you've brought the frequency under control and keep it steady, you're going to want to fine tune it and bring it back to as close to 60 as you can before the next disturbance happens. And the way that this is typically graphed, for a major power disturbance, this one's not too major, but 59.9 is a reasonably low frequency. So they lost some load. Primary frequency control steps in, and automatically generators respond and kick in more power. And I'll get to how it is that they do that in a moment. And then after they've stabilized the frequency, then we can begin the delicate task of gently driving it back to 60 hertz. Now, in reality, by the time we got back to 60 hertz, probably some other changes would have happened, because you never know exactly what the load is going to be at any particular minute or second. So you're constantly adjusting. This is one of my favorite stories from my hometown of Berlin. And it is the story of how the electric grid in West Berlin was a power island throughout my childhood. And I was blissfully unaware of this. Blissfully unaware because I don't ever remember the power being out. I mean, German engineering, man, the lights were always on. And what, in fact, the Berlin engineers were dealing with was a very small system, a very small island, where the frequency was varying pretty wildly about the nominal 50 hertz. because that's the best they could do, given that statistics was not playing in their favor, right? Whenever a big load turned on and off, it was a big per unit percentage of the entire city of Berlin, with, between 1 and 2 million people. So after the German reunification in 1989, they were going to reconnect East and West German grids, because during the Cold War, East Germany was connected to Eastern Europe and the Soviet Union. And there was a boundary through Germany where no electricity flowed. And both systems were nominally at 50 hertz. But it turns out that Eastern Europe actually practiced a tighter frequency control. They were more authoritarian about it and more precise. And so after 1989, after the wall came down, it was actually not possible to reconnect East and West Germany on the same AC grid, because the relay settings were all different and they wouldn't match. So it wasn't until 1994, it took them a few years to figure this out, and redesign their system a bit, that they were able to close the switches and reconnect everything. And this was sort of a big deal in 94, when West Berlin was reintegrated with the rest of, now all of Germany's electricity. And you could see that by virtue of being in a much larger system, which then is also connected to Europe, the volatility of the frequency became much less. And also that when Berlin would lose suddenly a generator, the frequency wouldn't drop down so far. So this is in the larger system, whereas in the islanded system, the loss of one small power plant would bring the frequency way down to 49 hertz. But we didn't notice this as consumers. We didn't notice this because all the relay settings were set to permit that, and the lights stayed on very nicely. So a little bit more detail now on how the generators actually work to keep frequency constant. I've just detailed here that keeping the balance of power is accomplished really over multiple time steps. And we're going to be looking at the second one, which is the governor operation, or what's called load frequency response. That's what those graphs have focused on. Of course, slower than that, we have markets. We have planning and unit commitment, basically scheduling which power plant is going to be on and off when, how are they going to schedule their power generation based on what we can forecast for the next hour or even the next few minutes, as we have a detailed weather forecast and we see that, at 3:54, the wind is going to stop blowing, so we're going to need to up a few megawatts. All that kind of stuff is handled by fancy computer systems. But then you get to a place where you can't really centralize this anymore, and you need to have some local feedback control that's robust, and that's actually been working even before we had computers for the whole, last 130 years, which is governor operation, where the generators are basically monitoring their velocity. And they're going to push a little harder if they see that they're slowing down, and they're going to push a little less hard if they see that they're speeding up. And the technology to do that was developed by James Watt back in the day for the steam engine, with a really simple analog system where this rate of rotation here, these two weights are going to fly apart as the rate of rotation speeds up. And it's going to pull on lever F, which pulls on lever B and on lever H. And then consequently, valve A gets opened or closed, which is just delightful. We do this with computers nowadays. And in fact, we can do a more refined version of that control. We can take into account the rate of change also. But the reason we have electric grids is that this technology was workable 100 years ago, totally analog, and very robust. I'm going to comment, before I go into this droop curve diagram, on the fact that there are also finer grained corrections to this governor operation or load frequency response. There's a rotational inertia in rotating machines that tends to stabilize the frequency over the course of seconds. And then there's a set of forces that operates really on the scale of cycles between generators, which is what holds them in lockstep and keeps them in alignment. And that's basically responsible for the fact that if one generator tries to advance its voltage phase angle, it's going to have to push a little bit harder. It's just like that rubber shaft. If you were going to push harder, your angle would be a little forward relative to the other rotating things that you're driving. So that, instead of being mediated by the material stiffness in the rubber, here it's mediated by electromagnetic forces on the generator rotor, which are not obvious. They're like three-dimensional, super hard to visualize, but it works, and we can come back to that. But the thing that we're interested in when we look at frequency data is basically how the frequency varies. And this is a little background here to understand how much power imbalance is associated with a certain amount of frequency variation. Here's a schematic of a conventional power plant steam turbine that has the governor on the rotating shaft, which sends a feedback signal back to the steam valve. There's a whole separate system for controlling the voltage magnitude at a generator bus. Someone asked about this in the Google Docs, and I began to say that, well, the voltage magnitude is regulated by the reactive power output, which is totally not obvious, and we can come back to that in another session. So we should assume the voltage magnitude stays constant, and all we're dealing with real power here is the angle and the frequency. This is a schematic of the old-fashioned drawing I showed you with the flyweights from the James Watt governor. But in this diagram, which is called the droop curve, what we're looking at is a setting where the generator automatically will output more power in megawatts, more steam, more cowbell, more force behind it, as it senses that the frequency goes down, and vice versa. If the frequency goes up, it'll back off on the power, and a given generator will have some range of where it has flexibility to operate. So by moving along this curve, the generator will be performing primary frequency control and helping stabilize the frequency. So if this generator is responsible for making up the difference in the system, and somewhere another generator drops off or a big new load shows up, this generator is going to see that the frequency has dropped. It's going to pick up the power and end up at this new location. Now, notice that in this new equilibrium, we've stabilized the frequencies. Frequency is constant again, but it's not at the value that we want it. It used to be 60, now it's 59.98. So now comes a secondary frequency control where we gradually adjust a screw on this contraption, and this is where the motor turns the screw. We adjust the set point of this thing such that the curve will slowly move back up. So this new power is now the desired power level for the generator, but we're adjusting the screw set point such that it will hold this power, but let the frequency come back up to 60 hertz. And usually you will have some large number of generators participating in this control. Obviously, as a system operator, you want to have a large, a large resource to respond. And the more generators respond, basically you add all these curves together, and then each one of them isn't going to have to do that much work for a given per unit frequency change. So frequency now can also be scaled in per unit. I'm going to skip these slides.
Can I just ask you about the measurement data that would inform that kind of control? it seems like anything. So if we'd be looking at higher frequency measurements than PMUs just to monitor the frequency, right?
Right, but remember that all this is basically done analog. So you don't record the data, you don't digitize them, you just have a contraption that responds, right? So in this case, your rate of rotation is being instantaneously measured by the separation of these flyweights, but nobody's recording this.
Interesting.
Now, of course, in the old world, you'd have some pen and ink, on the rotating, what do you call those? Plotters, right? So it would tell you what you've measured, but you can know all this because it's a strictly local measurement. You can know all this without fancy data communication. And that's really the crucial thing here, is that power systems have been operable because it's physically possible to do feedback control locally. And, after the Loma Prieta earthquake in 1989, Pittsburgh power plant operators basically kept a good chunk of the Bay Area energized after the lights went out in most places after the earthquake, just basically flying by the seat of their pants, allowing their old-fashioned, this is a power plant built in the 1950s and some other units in the 60s and 70s, but allowing these units to basically self-regulate using their analog controls. And it works. And, it worked long before we had computers. Now, that control system is not exactly easily compatible with advanced inverter controls. So that's a whole other subject. I mean, inverter controls, which are power electronics, and you can tell them to do anything you want them to do, and they will do it exactly, and they will do it quickly. But be careful what you ask for, because whatever the control schema is that you implement with your inverters may not play well with these legacy control systems. And that's a whole field of interesting research. I am going to, I think, it's 4:01. I'm going to show you just a couple more pictures on this topic, which is that there's a cutaway view of an actual steam turbine in the front and generator in the back attached to it. And when there are disturbances in the system, you will see this shock load and, the twist in what's here a little bit less than a degree, with a damped oscillation returning to a kind of more or less steady state, not exactly steady state. So this is the type of thing that used to not be observable. This type of diagram we now can see because there are PMUs, because while you could do velocity measurement analog, you couldn't do really a position measurement, because that requires just rapid measurements in fast succession and keeping track of them. So power engineers understood that generators do this stuff, and they understood that there's a quantity called inertia that sort of and internal really damping forces in the generator that help restore position and frequency to previous values, but they weren't able to empirically observe that. And what these generators do when there are big disturbances actually wasn't really known exactly until there were PMU measurements, and there can be some pretty nasty oscillations. What's interesting is that these things propagate, and that in this particular instance, there was a big generator lost in Southern California, and the frequency, if you can't see on your screen resolution, the scale goes from 60 down to 59.73. So that's right sort of near where you might trip some relays open. Now, in Southern California, the frequency only went down to 59.77, but because of the sort of way that the oscillation propagated through the network, some generators very far north in Canada that are ostensibly synchronous in lockstep with everything in the Western grid here, they oscillated quite a bit from this shock load. And this is something that grid analysts are worried about. And then there's the big question of, as we begin to replace rotating machines with inverters, will the inverters make this better or worse? And the answer is, well, we don't really know, and it'll depend on how we control the inverters. But how do we validate that we are controlling inverters intelligently? We need grid data measurements, and specifically PMU measurements for that. This is the classic event in 1996, if you're old enough to remember. The lights went out, and they went out because there were power oscillations that were underdamped between the north and the south. This is at the California-Oregon intertie. Grid operators were under the naive illusion that everything was going according to models and the power flow was perfectly steady. In reality, there was an oscillation which over time was underdamped and exploded in amplitude until the system disconnected. And what was so interesting about this event is that nobody saw it coming. And these data were then retrieved from Pacific Northwest Lab. Sort of in hindsight, they had some experimental PMUs, and they're like, "Oh, now we know why the lights went out." But so this is, this was a great motivator for putting in PMUs. It's 4:05. I'm happy to go longer, but I will pause for questions and a cue from Ben as to whether to continue.
I actually did have a question on the oscillation, the original oscillation slide. The y-axis was labeled degrees. Is that observing an oscillation? It was actually an earlier one. This one. So sorry.
Is this the one?
No, go down. Yeah, this one right here. So are we observing the oscillation in the angle, or are we observing the oscillation in the frequency?
Good question. We can observe it in either. Because if you think about a harmonic oscillation, so let's suppose that what we're looking at is roughly sinusoidal. The rate of change of a sinusoid is a sinusoid. The frequency is just the rate of change of degrees. So we should be seeing that same shape, whether we're looking explicitly at the angle or whether we're looking at the frequency, which is the rate of change of angle. There will be, some minor differences. And certainly, if we're looking at the degrees, we will get a better explicit sense of how things are different at different locations. But fundamentally, everything is going to be wobbling, whether you're looking at degrees, at position or at velocity. And in this graph, we're looking at frequency. And, the damped harmonic oscillation is basically the same type of deal. You would see a similar shape if you looked at the voltage phase angle in Alberta. Now, what's a little bit different is that the frequency you could measure locally without having to use the same clock. So you could generate a graph like this without PMUs if you recorded the frequency at each location and just synchronized it well enough to, the nearest, second or tenth of a second or something. You don't have to synchronize it to the milli or microsecond like with the PMU to be able to describe a relative angle. That makes sense.
It does. Is there a standard, so I guess, with the magnitudes, we're looking for sags or spikes. But when you look at the sort of frequency PMU data, mostly what we see is, periods of high variability in the frequency and then periods of more stable, frequency, and then it's kind of keep going like that over time. Is there a measure of stability in frequency that's commonly used, or?
Yes. So there's a thing called the ROCOF, which is the rate of change of frequency, ROCOF. But that really is mostly used in the context of a big disturbance. Like right here, you have a big bad ROCOF, right? Where over the time period of like 2 seconds, your frequency is dropping by a quarter hertz, which is a lot. I think what you're describing is more a metric of volatility. And I don't think there's a totally standardized metric of volatility. I mean, it's a thing that we looked at, for the Berlin example. So if we go to this one, right? So there's periods like this and periods more like that. That could be a matter of there's very uneven renewables. It's windy. Or not windy. Texas, ERCOT has a lot of wind power, and some of their frequency, time series sometimes look a little bit more sketchy like this. And it could be a matter of how well the generators that are online at a given time performing frequency regulation, how well they're doing that job. There has been a bit of propaganda in recent years about how we need coal-fired and nuclear plants to do frequency regulation, which actually our friend Alison Silverstein wrote a wonderful paper dispelling that myth. And it turns out that coal-fired power plants, and this wasn't in her report, but sort of related, coal-fired power plants are actually not very good at correcting this kind of jitter because they're too slow responding. In a coal-fired power plant, there's a lot of thermal inertia, and the instant that you measure the frequency slowing down or speeding up is not the instant that you actually deliver more or less power to the steam turbine because there's so much inertia in this system. So depending on which plants are online at any given time performing frequency regulation, you'll see the frequency be more or less jittery. And then depending on whether weird stuff happens with the load. I think a big test is going to be whether advanced inverter controls can be implemented soon enough that they can demonstrate improvement in the frequency response, as opposed to being a drag on the system and making, life harder for the grown-ups.
Awesome, thank you. How many slides would you say?
I got 6 more.
I mean, I think that if you're willing to stay on, that
Sure.
You'll see those last 6 slides.
Okay, let's go for it. These were just some illustrations of stuff we can measure with micro-PMUs in the real world. And, voltage phase angle will swing with a disturbance, just like voltage magnitude. So this particular incident did not end well for the squirrel, but it was a great moment for micro-PMU diagnostics. So we could show that a high impedance fault, which is not a very respectful way to talk about a dead squirrel, but a high impedance basically does not allow a lot of current to flow, which means that the circuit breakers aren't disconnecting or interrupting this fault. So basically the squirrel is going to cook until it's done and falls to the ground and the voltage recovers. So the current through the squirrel is the green line. That it's a little hard to follow here, actually, but there's a current spike. And then as the current spikes, the voltage drops because the squirrel makes a short circuit. And we can infer some things about the nature of the system from the ratio of the current to the voltage. But all of this would have gone undetected by old-fashioned SCADA measurements, and goes undetected by circuit breakers because there's just not enough current for long enough to, melt a fuse or trip a magnetic relay. So this is where the micro-PMU measurements came in very helpfully to be able to diagnose that, oh, maybe there's a place in the substation where, the squirrels jump over the fence, and, well, what are you going to do? But if it's trees, then, for example, palm fronds, then you might be able to take some remedial action. So this was a case where a big PV array tripped offline, and the utility thought that, well, maybe it was the inverter that was doing something wrong. But upon studying micro-PMU data, it was discovered that, no, actually, the PMU did everything exactly what it was supposed to do. I mean, the inverter did everything exactly as it had been told, because it was told to disconnect when the voltage drops below some per unit level. And the voltage dropped below some per unit level because there was a short circuit with a palm frond. So, go send the tree trimming crew out. Don't blame the solar array. And these types of, diagnostics are not relying on angle. Those are simply high resolution magnitude measurements. I showed you correlating voltage magnitude measurements on different phases in the Bay Area. This is only a single phase, but showing you the relationship between Northern and Southern California. And the fact that when there is a big fault somewhere that creates a big disturbance, you can see it in different places hundreds of miles away, which is kind of cool. And, again, these are small values per unit. Per unit is how you would compare them. No customer is going to notice this. I mean, this would barely be perceptible that the lights got a little dim for a tenth of a second or something. But in terms of diagnostics and being able to triangulate where did this originate, you would want a few more sensors distributed across the geography. But with NI for AI, a very cool capability to envision is that if there are enough participating sensors spread out geographically, that will pick up these disturbances, but they will pick them up in different amounts, sort of attenuated depending on their location. That means that it will really help say, well, where did the disturbance come from? And, for a local utility, that's a matter of a lot of money for being able to send repair workers there. On a larger geographic scale, presumably operators should already know whether a disturbance originated in Arizona or New Mexico or California, but it can't help to have sort of instant answers at your fingertips. Here's a more local type of diagnostic. This is observing what are called tap changers in transformers. So tap changers are mechanical devices that change the effective turns ratio of a transformer. And they do this to basically compensate for the fact that people's loads increase and decrease over the course of a day. And as the load increases, there's more voltage drop on a feeder, on a distribution circuit that goes down the street for miles. And so you can see as the load increases from 6 in the morning to the afternoon, the voltage as measured at the service entrance at Power Standards Lab sort of kept going down a few volts. And then there would be the tap changer at the transformer that basically changes the turns ratio by 1% or something. It moves a contact to a different winding, a copper winding on the transformer, and basically doesn't step it down as much from the transmission level. And so that step change raises the voltage up until more and more load drags the voltage down, and the tap changer operates again, and so forth. This is something that utilities are concerned about, is going to, those mechanical components are going to wear out if a bunch of solar inverters are going to be changing their output over the course of the day, and these tap changers have to go up and down as clouds pass, which they're not really designed to do. A handful of operations per day is kind of okay, but they wear out, and they're expensive to replace. And here, this was a question also. about, how do you diagnose a problem? Well, in this particular case, our colleagues at Lawrence Berkeley Lab noticed that there was, when you looked at the current, and actually, no, when the current is in green. First, they looked at just the voltage, and the voltage would sort of have these weird momentary sags. And they're like, what's up with that? And when they looked at current, it's like, oh, the current sort of jumps up. So this was an anomaly that really had no good reason for being there. And the utility went out and did a little health check on the transformer and said, ooh, this baby was sick. Thank you for bringing this to our attention. So this is actually a high value application of, asset health diagnostics, if you have high precision sensors distributed throughout your system. And then lastly, this was a question that was asked, how do you figure out how much solar is connected? And the answer is, well, if the solar isn't measured directly, all you have is a net measurement like we had from PMU1 that includes a bunch of loads and a bunch of solar generation, and you don't really know which is which. You can correlate that with insolation, sunshine data that you have separately. And even for a cloudy day, you can do a pretty good estimate in real time of how much solar is being generated. Grid operators are very interested in this because they want to know how much load is actually being masked by solar generation when all they can see is the net load. Because what if there were a disturbance event that caused this solar generation to trip offline suddenly? And in that moment, they would become painfully aware of all the load that had been offset by it. And they would have to be prepared for that contingency to supply that load from some other generation. So system operators need to know their risk exposure to the loss of solar. And they can't do it if the solar is behind the meter and isn't being, there's no telemetry. So applications like this have a pretty high value for system operators to be able to, estimate at any given moment how much solar is being injected behind the meter where we can't see it explicitly. And that is my last slide.
Well, that was wonderful, Sacha. Thank you so much. We really appreciate you joining us both these evenings this week and last week to discuss this.
Thank you for being the awesomest audience.
Does anyone have any final questions before we wrap up?
Well, feel free to ask any follow-up questions in that same Google Doc.
And like last time, this was recorded, so I'm sure everyone will be referencing this video as we start to dive into this data a little bit more deeply.
All right. Thanks so much, guys.
Thank you.
Have a good night.
Thanks, Sacha.
Thank you.
Thanks, Laurel. Bye-bye.
Thank you.